everyone, welcome back to alkaline hydroxide 784. And I'm kind of aware that the chemistry series is going to have really long episodes because just looking at the learning outcomes, well, it's going to be a long episode, I think. Hopefully, it's not too long. And today in the chemistry series, we are doing the second topic, it's chemical bonding. And it's under the core idea to structure and properties. So yeah, we're gonna go through the learning outcomes again. Right, so the first one is about the chemical bonds, and we're looking at the different kinds of bonds: ionic, covalent, and metallic. So all of the chemical bonds are electrostatic in nature. So but there are some differences between each of them. They all involve some electrostatic attractions, but the way it works is different. I think you should know that by now. So in an ionic bond, you have like a positive ion and you have a negative ion. So you have the cation and the anion, and they are attracted to each other because it's positive and negative. So that's the idea, like the electrostatic attractions between the positive charge and the negative charge. That's how ionic bond works. And the covalent bond is you're sharing the electrons instead. So in this scenario, the attraction is actually between the pair of electrons that is shared and the positively charged nuclei of the covalent atoms, in the sense, because when the electrons are shared, like it's kind of, it's not completely in custody of that one atom or the other atom either. So they both become a bit more positive in a sense, and there's attraction between the electrons and the two nuclei. And the third one is metallic bond, and it in this scenario, when you draw it out, you already draw like positive cation things. Like for the atom part, you draw the cation and then you draw the electrons as dots. So the attraction is between the positive cations and the delocalized electrons. Yeah, that's what a metallic bond is. Okay, so the next one is describing ionic bonding, covalent bonding, and dative bonding, or coordinate bonding, if that's what you call it. And you had to use dot and cross diagrams in describing this. Okay, so for ionic bonding, well, for ionic bonding, how would you would describe it in a dot? Actually, show it in a dot and cross diagram is, for the positive atom, that you don't have like electrons in the outermost, so-called outermost shell, in a sense. So you don't actually draw any electrons for the cation. So you just draw, like for example, the sodium, then you bracket it and put a plus or something, sodium plus. And then the right. So if the chlorine atom has a full orbit, like the full outermost electron shell, in the sense, it will have 7 of its own electrons and 1 of the sodium electron, in the sense, which you would represent with a different symbol. So you only have 2 dots and crosses. So you can either draw like 7 dots and 1 cross, or you can draw 7 crosses and 1 dot. And that whole thing will be bracketed and you can put a negative on it. And you can do this with any of the ionic compounds that you have. Technically, for A level, you're allowed to do that. And how do you describe it? Well, ionic bonding. Okay, what do you mean by describe? We already described it just now, technically. Between a sodium, in sodium chloride, the ionic bonding is between the positive sodium cation and the negative chloride anion. And yeah, that's pretty much it. I don't know how else to describe this, but yeah. So the chloride has the so-called full orbital because of the electron from the sodium, and therefore the chloride is negative. The sodium lost one of its electrons, so it's positive, and now they have a attraction towards each other because of that. Okay, cool. So the next one is covalent bonding, as in many covalent compounds like hydrogen, oxygen, nitrogen, chlorine. Okay, basically I just put a whole list of stuff here, but you get the idea. So covalent bonding, you can you just need to know how each of the covalent compounds are actually connected to each other. Like if it's hydrogen, you know it's two hydrogens next to each other. If it's water, you know that there is a H2O in the sense, like the O is in the center. You should know at least that. Like you don't draw H2O as HO, like that's not how you draw it technically. So you just need to know how, in what order the atoms are connected, and to which extent the electrons are shared. So like whether it's one bond, two bonds, or three bonds. Like is it single, double, or triple bonding? So for example, in H2O is single bonding, but CO2 is double bonding. So you should reflect the number of shared pairs based on the number of bonds between the two atoms in the sense. So for example, for a single bond like in H2O, you will just put a cross and a dot, and that's one pair, simple as that. Don't put any more extra stuff in between the two of them. But if it's carbon dioxide, you need to put two crosses and two dots. Then you'll be representing a double bond. Yeah. And then the rest of them should be around whatever atom they're supposed to orbit, or like supposed to belong to in a sense. So that's covalent bonding, and you just describe it the way that we did in the first learning objective. So I think you already get how to do that now. So there's an attraction between the pairs of electrons here and the nuclei for whatever compound it is. And the third one is the coordinate bonding, which is quite different from covalent. Which is a bit different from covalent bonding, because in covalent bonding, it is each of the atoms will give one electron to be shared. But in coordinate bonding, it is technically covalent bonding, like you're sharing a pair of electrons, but in this scenario, it's not both of them contributing, but one contributing the entire, like the electron in a sense. So the easiest place to see it is the ammonium ion as well as the aluminium chloride molecule, the dimer of the aluminium chloride in the sense. So for ammonium ion, which is even more well known for this whole thing, you know that it's actually, you know, NH3 is ammonia, and once you add another H, it becomes NH4 plus. So why does it become plus? Because you're actually kind of, you know, let's just put it this way, like the nitrogen has got 5 electrons, and once you put 3 hydrogen that's already filled up, the nitrogen can't really take on more electrons for now lah, unless it wants to do some weird things. But if it wants to be a bit, if it still wants to have only 8 electrons in its outermost shell, and you have another hydrogen coming along that way, then the hydrogen has to lose its electron and become a proton. So it's now hydrogen plus. And when you combine the hydrogen plus with the NH3, the pair that is actually shared between the N and the H is the one that belongs to nitrogen already. The 2 electrons that's already there as a pair in nitrogen. So it then becomes NH4 plus because the H doesn't lost its original electron. So the overall charge is +1, basically. Yeah. And in Al2Cl6, which is the dimer of Al3, so in aluminium chloride covalent compound, yes, it is a covalent compound. It's not an ionic compound, despite there being aluminium, as you would originally think. How this actually works is aluminium is group 13, I think. Yeah, group 13. So so it has 3 electrons. Yeah, if you think about it that way, 3 electrons, and chlorine has 7 electrons. And since aluminium only has 3 electrons, it can only really bond with 3 chlorines with its own electrons. And once that happens, you can have 2 of these molecules that use since chlorine has a lot of electrons, right? The chlorine in the end gives a dative bond with it does some dative bonding with the aluminium to create a dimer. And there you get your Al2Cl6 dimer in the sense. which is pretty cool, I think. Yeah. So if you're looking at dative bonding, if you're doing a dot and cross, you just show that both of the, like, the pair of electrons is, they're both crosses or they're both dots in the sense. But if you're looking at it in the diagram where you're just drawing lines, for a dative bond you draw a arrow instead of a line. So that's the difference. Okay, so so for the covalent bonding, if yeah, so the next learning outcome is describing covalent bonding in terms of orbital overlap. And in this in A level you're only looking at s and p orbitals. So we're gonna look at sigma and pi bonds in the sense. Okay, so when you have s orbitals overlapping, well, there's really only one way that you can think of it overlapping, which is like just, two of them, they're like both spheres. Imagine you had two balls smushed against each other, and that's what you get. So they just become like one, I don't know, cylindrical kind of orbital shape, I guess. It's like a head-on overlap. And for a p orbital, it depends on which one it is, or like which way they overlap. So they can either overlap head-on or they can overlap sideways. And when if they're overlapping head-on, it's usually with an s orbital, because the s orbital can really join the other side of the p orbital. And if it's sideways, it will be two p orbitals overlapping with each other. And in the s orbit, if it's like the very first bond, a single bond, you would be only getting a sigma bond. And if it's not, if it's a double bond or a triple bond, you would be having a sigma bond as well as one or two pi bonds, depending on whether it's double or triple bond. So the sigma is always present, but the pi bond is based on whether a single bond or double bond or triple bond in the sense. So yeah. So the next point is about um let me see. Okay, so next point is about the shapes and bond angles in certain molecules. And this is based on the VSEPR, or the valence shell electron pair repulsion theory. Yeah. So of course the way that we actually remember the theory is more of, we look at the base pairs and the shared pairs, I think. Kind of, yeah. So uh so the bond pairs and, sorry, base pairs and lone bond pairs and lone pairs, I think. Yeah, that's what you're looking at, sorry. So the pairs that are actually shared and the pairs that are just belonging to the atom to begin with. So for there's like this whole table where you can see how the number of each of them kind of defines the shape. So what I'll just do is I'll just explain some of the shapes of the examples that's actually given in the curriculum. So I mean the syllabus guide. So the first one is boron trifluoride, which is trigonal planar. And why is that the case? Boron is a bit electron deficient in its outer shell, even with 3 fluoride in it. So boron has, let me think, beryllium. Yeah, boron is like aluminium, kind of. So yeah, is it? I think so. Yeah, so boron has 5 wait, no, sorry, boron has 3 electrons, and fluorine, only 3 fluorines can actually attach to it, just like how aluminium can only have 3 chlorines attaching to it. So in that scenario, it still lacks electrons after the 3 fluorines attached to it, and overall it only has 3 you know bond pairs. And since they're all bond pairs, they kind of repel each other equally, and you get like this nice 180, sorry, not 180, like um what can I say, You get like this nice, like imagine if you have a circle and you cut it into 3 pieces equally, like those pie charts, and that's the kind of that's the kind of shape that you're supposedly getting here. And it's called trigonal planar because it's in the same plane. You don't need to change the plane or anything. This is all single bonding, so there's no weird plane changes here. And so the next one is CO2. And why is it linear? So CO2 only has two regions of bonding for that matter. Oh yeah, that's the other important thing you need to know. How many regions of bonding there are. Or like how many regions of electrons there are in the sense. Electron pairs in the sense. So in CO2 there's only two bonds, and the rest of there aren't any free electrons. All of them are used for bonding. And therefore it is literally like a straight line. It's linear with an angle of 180. And for the next one, CH4, which is tetrahedral, once again all of the electrons are used for bonding, but in this case you have 4 bonds. So when you have 3 bonds you can still do a trigonal planar thing, but when you have 4 it doesn't, like, the most efficient distribution of the bonds is a tetrahedral shape. That's just how it is. It's like mathematically that's how it works. So that's why it forms a tetrahedral shape, so that you can actually have 108. So 108-ish, yeah, 108, 109 degrees separation, rather than a very forced 90-degree separation, which is what you would get if you were to force it into a plane. So now it becomes a bit more 3D-ish in shape, a tetrahedral shape. So now we look at NH3, which is trigonal pyramidal. So instead of trigonal planar, it's trigonal pyramidal. And the reason here is because you know that nitrogen has that one lone pair of electrons, when you're talking about the ammonium ion. So here is just ammonia, so you don't have the extra H meddling in here. So that last pair of electrons is going to be considered as a region as well. So it is somewhat like a tetrahedral shape, but because that pair of electrons is not a bond pair but rather a lone pair, you don't really see a full tetrahedral shape per se. You don't have anything sticking up above the end. It's not an ammonium ion, it's still ammonia right now. So instead of calling it tetrahedral, we call it trigonal pyramidal. So it's like the tetrahedron without the top part, basically. Yeah. And the angle is a bit different because of the lone pair. The lone pair has a different repulsion compared to a bond pair. So next would be the water, H2O. H2O is actually kind of like ammonia, but there's one less bond pair. Like one of the bond pairs is now another lone pair. So H2O actually has 2 lone pairs, and the shape that you get is like a weird looking version of tetrahedral, but since 2 of the pairs don't have anything sticking out of them, it just looks like a bent atom. Basically it's bent, that's what it's called. And the next one is SF6. For the angles, there's slightly different angles. There's like 109, then 107, 105. So the more lone pairs there are, the smaller the angle will become, because the lone pairs are a bit more, lonely, and so the repulsion will be greater. So in the bond pair, the electrons are shared equally amongst the atoms, and they'll be pulled towards one, like the pulling, the attraction towards the central atom will be a bit lesser compared to the lone pair, because it doesn't have full custody over it anymore. And therefore the repulsion is a little bit lesser compared to the lone pairs in a sense. So for SF6, which is octahedral, we know that sulfur, well, it is kind of 6, I suppose, like oxygen, I guess. And since it's SF6 and it can really extend its orbital because of the fact that it's in the 3rd period, it can do that whole thing with using its d orbitals to expand and to accommodate a lot of electrons. it can then form 6 bonds. So in 4 bonds you don't need to do that 90-degree thing, but with 6 bonds that's the only option you have, because yeah, that's really the only, that's the easiest, that's the most efficient way to distribute 6 lines in, I don't know, a spherical space in a sense. Yeah, so that's how you figure out the shapes of atoms. I mean, sorry, not atoms, as in molecules, as well as their angles. So the angles, if you want to remember the exact numbers, you can refer to your notes, I suppose, or you can just kind of theorize it to some extent. At least know the generic one for the best case scenario in the sense. Yeah, so like for example, if octahedral 90, then the tetrahedral is it 109, or I don't know, 109, and then trigonal planar is 120 and all that stuff. Yeah. So the next one, yeah, so once you know that these molecules are like that, like the next learning point is to find out analogous molecules and predict the same shape and bond angle for those molecules. So you have to like uh, now that you learn why these molecules have a certain shape, you must apply it to other things and then see, oh okay, this molecule actually kind of looks like how water looks like, so it should work the same way, kind of. That's how you predict. So like for example, if there's another molecule that's just like water, it has like 2 lone pairs in the center and then there's um two bond pairs as well, it's probably like water in a sense, and there's no other regions of electrons in the sense, then it would probably have a bend shape with that same angle in the in its main in terms of the main atom, the middle one. So you can use that to figure out what the shape of molecules, like what kinds of shapes and angles certain molecules have. And of course I know there's one really cool program, like one of those fun the PHET, that one you can find one, there's one that you can look at the angles and shapes of various molecules there. So if you want, I can put a link to that below. Hopefully I'll actually do that and remember to actually do that. Right, okay. So the next learning point is bond polarity using electronegativity. And in bracket it says quantitative treatment of electronegativity is not required. Okay, so you don't really need to know the absolute value of the electronegativity, but we need to know which one has more electronegativity than which, in a sense. So so what is electronegativity? How do you express electronegativity? Well, it is kind of like the affinity for electrons. So it is somewhat opposite to how ionic, like IE, works, in the sense ionization energy works, because if you think about it, when the IE increases, electronegativity wait when the IE increases, electronegativity kind of increases as well. Okay, actually that makes sense. It's not really opposite, it works together. I mean, technically electronegativity is of a greater magnitude when the IE is greater. Because if you think about it, if it takes more effort to remove the electron, it means that the atom likes the electrons, right? So logically speaking, electronegativity is more for that particular atom or element for that matter. Okay, so how do we deduce bond polarity from electronegativity? So the idea is that you take the two components of, like the two atoms on the both sides of the bond, and then you see what their electronegativities are. Of course here you'll probably just have some value that's like 4 for fluorine, and then all the others are based off of that. So you just use those values and then think about it in that scale, because I'm not sure what the actual value of electronegativity, how you're supposed to represent it with a certain unit or something. That's why they use this number instead, like 4. And then it's like how you call diamond having a hardness of 10, and then I mean that one actually has a scale also. I don't know. Anyways, you get the idea. So fluorine is 4 and everything else is lesser than 4. So yeah, that's pretty much it. So you just minus, Like you find the difference between the electronegativities. And if you think about it in an ionic compound, like for example sodium chloride, the electronegativity difference is very huge. So it's actually ionic. So if it has a very huge, the more electronegative atom will electron from the less electronegative atom, and therefore it kind of permanently becomes like an ionic bond. Like one of them will always be having electrons and the other one will always not be having the electrons. Versus a covalent bond, which is like the other end of the spectrum. Yeah, kind of like the other end of the spectrum, where the electronegativity difference is quite small, so it's very easy for the two atoms to share the electrons rather than one taking it all for itself in a sense. So that's how electronegativity kind of works. Yeah. But of course, in the sense of certain molecules that are actually, like there's some ionic molecules that have more covalent properties and there's some covalent molecules that have more ionic properties, and that is what we're going to look at in the following, you know, in probably the follow like later learning outcomes. Okay, so the next point is deducing its polarity using bond polarity and molecular shape. Oh, this is the polarity of an actual molecule. Okay, so um, since we are looking at molecular shape, we're actually usually looking at a covalent molecule because ionic molecules have their ionic compounds have their own shapes in a sense. There's a lot of these crystal structures. And luckily you don't need to know this for A level, so it's okay. They have their own packing, ways of packing and all that. So yeah, that's how it works for ionic compounds. But for covalent compounds, you can actually have simple covalent compounds and have like discrete molecules, and each of them has their own shape in the sense, like the different compounds have their own shapes. Okay, so how, like, what is the meaning of this learning outcome? Basically, you get the you first draw the molecule in a 3D shape, or at least imagine it in a 3D shape, and then you think of whether the molecule has any overly polar bonds. Like the polarity of the bond is very high. Oh, so wait, so that's actually about the bond polarity. Oops, never mind. So yeah, if the electronegativity difference is high enough, yeah, you get a pretty polar bond. So it's like it's not ionic yet, but it's still a covalent bond but with ionic properties. It's actually a polar bond usually, and polar bonding occurs with usually with the most electronegative molecules, which would be F, which is fluorine, O, which is oxygen, N, yeah, and N, which is nitrogen. So FON. That's where you usually see the polar bonds in the sense. And if it's very polar in that sense, like in those molecules, then you can, for example, you can say that electron will all be going towards the O kind of. So you draw an arrow pointing towards the, like showing that okay, this is where the electron density is. And in a water molecule there is a certain polarity to the water molecule. And the hydrogen ends will be positive. So there's actually this overall polarity because water molecules aren't linear, they're like bent. So the overall polarity actually points upwards because, is it upwards or like how does it, the pointing is towards negative, I think. Yeah, so it all points in one direction. So it's more negative on one side, more on positive on one side, like a magnet. And that's why you can actually do that whole thing with water where you attract it with some magnet or something, and then the water kind of bends or some, like the stream will bend. That's why it does that. Because it's actually like polar, like it has this dipole effect in the sense. So likewise you can do that with other molecules and then see which ones actually have a net polarity in one direction. Like if you think about it, if something like carbon dioxide isn't polar because the the molecule is linear. So like the C is in the center, the O's are at the ends, so they're both negatives at the ends, and the polarity kind of just cancels out. Then it's no longer like dipolar in a sense, or bipolar in a sense. Yeah, bipolar or dipolar. I don't know which one is the right word. Okay, never mind. It's not a dipole and it's not bipolar. Okay, that was weird. Okay, so yeah, that's how you do it. You just see where like you think of it like vectors. If the vectors cancel out, then it's not polar. But if they don't cancel out and there's this very strong one that's pointing in one particular direction, then it has a pole in a sense. It has the dipole. So the next learning outcome is describing the following forces of attraction, electrostatic in nature. So the first part will be intermolecular forces, and the second one will be hydrogen bonding. Okay, so intermolecular forces based on permanent and induced dipoles, as in CHCl3 liquid, bromine 2 liquid, and the liquid noble gases. Okay, so intermolecular forces, they're referring to PD and ID. So yeah, we already know where we're going with this. Yeah, so if it's something like CHCl3, it has a it is like one of the ends is hydrogen, so it's like a tetrahedral shape, but one of the ends is hydrogen, so there is actually a polar moment to it, and therefore it has a PD kind of attraction, so it's like a polar molecule. And since it's a permanent dipole and you can find another one of those molecules which is another permanent dipole, they will then have the attraction automatically in the sense, because they're like two magnets coming together. For the other ones, which is like bromine and liquid noble gases, they are more of induced dipoles, so which is ID. So ID occurs when the electrons will keep moving. So there will be this point of time where they tend to concentrate in one side of the atom. It's possible, it happens. There's like a lot of chances of that happening. So when that happens to two different atoms that are next to each other, or molecules for that matter, they will become like dipoles for a very small period of time. So one of them will become a dipole first, which is the instantaneous dipole, and then the other one will be induced by this instantaneous dipole. So the other one is an induced dipole. So the two dipoles then attract each other. That's why it's called ID. Induced instantaneous dipole, induced dipole, which is different from permanent dipole. So it's just describing the two things that are attracting each other. So yeah, that's how you remember it without having to memorize stuff. You remember it as what exactly is attracting each other, kind of. So yeah, the next learning point is outline the importance of hydrogen bonding to the physical properties of substances, including ice and water. Oh, we forgot about hydrogen bonding. Oops, sorry. Let's talk about that first before we come to the ice and water part. Okay, so hydrogen bonding is a very special form of polar bonding, where you have a hydrogen atom as well as a polar, like a very highly electronegative atom like O or N or F. Okay, so in this scenario, you need the O and the H. You usually have the O and H together, and you need two of them, like two of those molecules, to have the hydrogen bonding. So the H from one of the molecules will attract the O of the other molecule, because the H will be slightly positive and the O will be slightly negative, and that's where you get the bonding. And it will work with N as well. So that's how it works. It's pretty straightforward because we already talked about it, kind of. The O pulls the electrons towards it because it's highly electronegative, so it's slightly negative, and the H now is slightly positive, and therefore they kind of attract each other, like in different molecules they will attract each other. Okay, so now let's look at it in terms of the physical properties of ice and water. Um, well, ice is a crystal, I guess. It's a nice solid crystal. And I think there could be this sense of how the water molecules pack together because of the dipole effect, like the dipoles in water, and that allows ice to nicely crystallize, I think, to some extent. And uh, yeah, that's just how it is. So wait, what other physical properties are we looking at? I know water you can bend it using a magnet, that kind of stuff. I think you can see that. And then water you can easily, like when you dissolve a salt into it, the salt actually dissolves by, like the ionic compound dissolve by becoming surrounded by water molecules because of the whole positive and negative charge thing. Yeah. Yeah, that's pretty much as much as I can really think of. What kind of physical properties are they looking at here? I don't know. Yeah. But yeah, you can kind of see where this is going. Oh wait, is it like the boiling point of water or something? Is that what they're talking about here? I don't know. To just simply only covalent bonding. And that kind of makes it easier, like it makes it harder to boil water compared to some other molecules that have a similar structure to water in a sense. Yeah, like basically something, H2O, right? There's a H2S as well, but H2S is a gas. H2O is liquid at room temperature, so uh, you can see the difference in boiling point there. Okay, so compare the reactivities of covalent bonds in terms of oh wait, before that we look at the bond energy and bond length for covalent bonds. Okay, so bond energy is the energy that you require to break the bond, and when you're writing it down you have to specify like 1 mole of that molecule or compound or whatever, like 1 mole, like many bonds basically, and you probably had to put the standard conditions, so yeah, that's pretty much it. And bond length would be the length of the bond, technically, like when you, I don't know how they measure it, but like the length between the two atoms when in terms of the bond. Yeah. So the reactivities of covalent bonds in terms of bond energy, bond length, and bond polarity. So you can use those things to compare the reactivities of covalent bonds. Okay, so if the covalent bond has a higher bond energy, it's a bit harder to break it, so it's less reactive in a sense. And if it has a smaller bond length, it's usually because it has a higher bond energy. So the two atoms tend to be nearer to each other, or it could be because it's a double bond, triple bond. So it's a bit more beneficial to bring them nearer so that the bond is more secure. And as well as the bond polarity may influence the bond energy because if or it can influence the reactivity as well. So if the bond length is very large, it might be more susceptible to outside things reacting with it. If it's very close to each other, there's lesser, I don't know, there's probably lesser space to actually react, I guess. And bond polarity will also determine how it reacts. So, if it's very like negative on one side and very positive on one side, then other negative and positive things can actually react with it in a sense. So, yeah. That's why like nitrogen is somewhat neutral. It has a triple bond, which is quite short in bond length, and it's not really polar in any way, so it's very unreactive compared to the other. Of course, if you're looking at oxygen, it is also not polar, but oxygen is very reactive because it's oxygen, I guess. You can easily, I mean, not very reactive. I don't know, there's just some bonds that are more reactive than others. So describe in simple terms the lattice structure of a crystalline solid, which is ionic, as in sodium chloride and magnesium oxide. so the so the lattice structure would be, yeah, it's just the, the alternating ions in a big crystalline structure in the sense. That's pretty much it. There's nothing else much to really say here because the details of that are not really required. You just need to know that it's in this crystalline um, giant ionic structure, like giant crystalline structure, and it's like usually alternating when you look at it. So for simple molecular, it is it's simple molecular, so it's not giant anymore. It's just one like discrete molecules in the sense, like iodine for example. And then the third one, giant molecular, it is a crystalline, like a giant crystalline structure. And for this you actually need to specify how it's attached, like how the bonds work here. So for diamond, it's all of the four carbon bonds are being used, so all the electrons are occupied in bonds. As for graphite, only three of the bonds are formed, so it forms like a hexagonal structure. And the last remaining electron there, like the rest of the electrons will form some kind of ID. Is it ID? I guess they have this sense of bonding between the layers, so that will give graphite its the conductivity in the sense, because there's all these free electrons that it's kind of delocalized as well. In a way, like, it's kind of like delocalized electrons, because the others are already kind of bonded. This is the only free one. Then the fifth one is hydrogen bonding. Okay, so for hydrogen bonding in ice, yeah, I guess you can think of it as like when water molecules come together, you have to think of how the positive hydrogen will bond with the negative oxygen of the other molecule in the sense, and in that sense it will form a crystal structure. It can be a decently big giant structure as well. And then metallic bonding, it was also somewhat giant structure. But in this scenario, instead of looking at it as simply just things being bonded to each other, you have like the cations in one crystalline structure and all the electrons floating around, like this is a sea of electrons. And when you describe all of these structures, it would be helpful to describe the bonding and where the attraction is. So as we saw in the very first learning outcome, you should mention that here. Hopefully, I guess that will help make your answer a bit more complete in the sense. So where exactly electrostatic attraction is. Okay, so the next learning outcome is describe, interpret, and or predict the effect of different types of structure and bonding on the physical properties of substances. Um, oh yeah, there's a lot of things I can explain. Oh my. Okay, so let's start with ionic because we went in that order. It's follow the same order. So ionic, well, it conducts electricity because of the fact that there's positive and negative charges. But is it but the way, in order for it to conduct electricity, it needs to be molten, because if it's in a solid form, then the charges can't really move anywhere. They're like kind of locked in place, flow in a sense. Apart from that, ionic bonds are very strong because if you think about it, all the electrons are in one place, and the other side doesn't really have the electrons on the outer shell, that outermost orbital or shell, whatever they call it. So the bonding is very strong in terms of ionic bonding. As for simple molecular, oh yeah, so since ionic bonds are quite strong, they also have high melting point, yeah, in that sense. So it's quite that's just basically the kind of property that you get from having a pretty high energy bond in the sense. Okay, so for simple molecular, we know that since they're simple molecular, they're already discrete molecules. So they don't really have like a high melting point generally, because the molecules are already discrete. So the bonding between them is a lot weaker than ionic bonding or covalent bonding. Of course, the bonding within the molecule is definitely very strong, which is covalent bonds, but they don't, I mean, you're not going to try to separate the molecule though. So usually the melting point isn't about separating the molecules, but rather like separating the atoms from the molecule, but rather separating the molecules from each other, which is very easy to do when it's simple molecular, because the intermolecular bond, intermolecular bonding is somewhat weak in a sense. Yeah. So if you're looking at giant molecular bonding, like ionic bonding, giant molecular bonding will have strong covalent bonds in between the individual things that you need to break if you want to melt it or something. So that's why it's actually very hard to melt diamond, or let's say even graphite, let's say, because there's actually strong covalent bonds standing in the way of melting them. So that's why it's very hard to destroy diamonds. It's just hard to do it. They have like really strong covalent bonds. And of course, the difference between graphite and diamond is that graphite has layers of carbon atoms, and that's why graphite is quite soft. So the layers between the layers, there's like very weak bonding, but within the layer it has a very strong bonding, which is why you can create something like graphene, which is a single layer of graphite, and that thing is super strong. But if you're looking at graphite itself, which is comprised of multiple layers, it's very easy to remove the layers from each other in the sense. And of course, the fact that there's this free electron also gives graphite the electric conductivity, unlike diamond, which has all of the electrons being used in bonding. So they're all in place. They are not mobile in any way. So for hydrogen bonding in as in ice, um, okay, so hydrogen bonding, if the since it's hydrogen bonding, right, if the molecule is actually in a mobile state, like it's liquid or something, it could conduct electricity to some extent. But yeah, of course hydrogen bonds aren't as strong as covalent or ionic bonding, so it's a bit easier to melt those things compared to ionic or covalent, giant ionic or giant covalent structures in a sense. Yeah. So the last one, metallic. Metallic has metallic is somewhat hard to melt as well, because so you can think about it, the electrons are literally all around the cations, and that means that, wait, what am I saying? Okay, anyways, yeah, but the metal bonds are between the thing that you actually want to separate when you want to melt it. So since metal bonds are also pretty strong, it's quite hard to melt a metal. Well, some of them have pretty weak metallic bonding too. So it kind of depends on the charge density of the metal ion and all those certain other factors as well. So the other thing about metallic bonding is that you can actually, you know, can you can kind of bend it into various shapes and all that, because it's malleable. So the malleability of it comes from the fact that metallic structures are literally just a whole bunch of positive ions. So they have a sense of like the positive ions themselves kind of repel each other lah. But so when you kind of hit in one side of it, it's easy to slide. It easily slides. Like they don't have like a physical connection with each other. They only have an attraction to the electrons in between them. So it's very easy to bend it into other shapes. Unlike ionic bonding, where the individual atoms or whatever that is have bonding to each other rather than to a unifying kind of solvent or electrons in the sense. So it's a lot. So when you break it, metals have that special property that we can change their shape, given that we do not exert too much force, but we exert just the right amount of force to bend them and not break them. And I think most of the cases it's possible to do that without any issue. Okay, So the last learning objective is to suggest the type of structure and bonding present in the substance from a given information. So usually the information that you get is high melting point or something like that. And also some of the other things that I might have mentioned here, like how easy it is to change its shape or something like that. Like there could be many different things that there could be certain information that would allow you to know that, oh, okay, this is the thing that we want. So yeah. um so in that sense, yeah, you can kind of look at the information and then infer for yourself. Okay, so this is this particular kind of structure. This has this, like a certain, either has a very strong bonding or very weak bonding, or kind of bonding it has, and from there you can deduce that what kind of compound it might be, or you can just suggest what kind of structure or bonding it has in a sense. So yeah, I hope that was somewhat useful, even though I kind of, maybe I might have rushed through some of the learning objectives, I'm not sure, or I might not have given enough details, but if there's anything you want me to elaborate on, please do comment below. But if you found this video useful, nevertheless, you can press the like button and subscribe. And with that, I would like to say thank you and bye.